that van der Linde referred to yesterday. So I'll be talking about the theoretical physics approach to these problems. What happened historically was, in about 1991, I was made aware by Michael, amongst other people, that mathematicians were interested in this problem of the probability of a crossing cluster. And I've been working on related problems in statistical mechanics, applying methods of conformal field theory since about 1984. And I went away and I thought about this problem a bit, and then I realized, oh, I know how to do that. So I was able to write down a formula for the probability that there exists a crossing cluster. So that's something that I'm going to be talking about. I should explain, though, in the 25 minutes, or now even less, that I have. Obviously, I can't go into any of the technical details, so all I can really do is to give you some kind of flavor. So just to set the scenario, what we're interested in is some kind of finite region of the plane enclosed by a simple closed curve. In this case, I've just taken it to be a rectangle because that's easier to draw. And we're interested in a percolation problem at the percolation threshold, and we're interested in clusters which cross from one arc of the boundary, which in this case is C1, C2, one edge of the rectangle, to another. And I will call NC the number of distinct clusters which do that. And I'm interested in things that involve the probability distribution of this quantity NC. So the way that I, as a theoretical physicist, thought about the percolation problem was, in fact, as a special case of the random cluster model, which is equivalent to the Q-state Potts model. So I'll just very briefly go through that. In the Potts model, you have variables at the vertices of a lattice which can take q possible states. You have some probability measure on this, and you're interested in computing the partition function. This probability measure is basically a product over nearest neighbor links on the lattice, and it takes one value if the spins on the vertices at the end of this lattice are in the same state, and it takes another value if they're not in the same state. And so you can write it in this particular form here. And now when you expand out this product and you take the trace over all the possible values of the spins S, you end up with the partition function of the random cluster model, in which you sum over all cluster configurations on the lattice with a weighting p to the number of open bonds corresponding to, well, I may have got that wrong way around anyway, 1 minus p to the number of closed bonds, or the other way around, it doesn't matter. And q to the number of clusters. So the interesting thing about this is, although the original formulation of the Potts model was obviously only defined for integer q larger than or equal to 2. This gives you, on any finite lattice, a polynomial in q, which can then be evaluated at q equals 1, and then you're weighting each cluster with a weight 1, and that's precisely what you want to do for the percolation problem, the bond percolation problem. Now, it's interesting, though, of course, if you just put q equals 1, the partition function for the percolation problem is just identically 1, because you're just summing over all events weighted by their probability. But you can get interesting quantities if you impose different boundary conditions on the spins. For example, you can imagine a part of the boundary here where the Potts spins are free, and in that case, any spin in the when you sum over all possible values of the spins within that cluster, you get a weight q, as we had previously. But if you imagine a boundary condition where the spins on the boundary are fixed into one particular state of the Potts model, then all the spins in that cluster can only take that one value, because those delta functions fix them to be all with that value. So in that case, you get the weight 1. Of course, these are identical at q equals 1, but we're interested in trying to see how these depend upon q as q approaches 1. And this then gives us a very simple way of computing the crossing probability, the probability that the number of clusters is greater than 0, in terms of partition functions with different boundary conditions on the left and the right edges. So the top and the bottom edges, the spins are taken to be free, but we can consider fixed boundary conditions on the left or the right, and we can either consider the boundary, we consider the state on the left and the right edges to be the same state, say A and A, or we can consider it to be different, say A and B. And then this very simple argument illustrated by these diagrams here shows that in the case where you have a crossing cluster, it can't contribute to the partition function in the case where the states are different on the left and right edges, because by definition, all the spins in this cluster are all in the same state. Therefore, you can write down this very simple equation that says that the crossing probability is just the difference of the partition functions with the same boundary conditions on left and right, minus the partition function with boundary conditions being different. So what the theoretical physics approach to this problem is to try to get ways of evaluating these partition functions in the scaling limit. If you're interested in the mean number of crossing clusters, you can do something slightly more complicated. In this case, you can divide all the clusters into four different types. The first type are the crossing clusters, which I talked about. The second type are called 1, the ones which touch the left edge but do not touch the right edge. Type 2, which touch the right edge but don't touch the left edge. And type B for bulk, which don't touch either. And then by fiddling around with the boundary conditions on left and right, for example, ZFF means we take free boundary conditions both on the left and the right, so that all types of clusters are all counted with weight q. So we think of this as the expectation value with the percolation measure of this quantity here. But by, say, playing around with the boundary conditions, we can get different things, because once we fix the spins on either edge, those particular clusters get counted with weight 1 rather than with weight q. And then by taking a derivative with respect to q of this particular ratio here, and using the fact that, in fact, that at q equals 1, all these partition functions are the same, they're just equal to 1, then the expected number of clusters is given by this formula here. And notice, though, that you've got to take a derivative with respect to q in order to do it from this point of view. So, in a sense, from my point of view, at least, calculating quantities like the mean number of clusters, you can't work just in the q equals 1 Potts model. You've actually got to go away from q equals 1 in order to do that. Now, what the conformal field theory ways of calculating these correlation functions involve is something called boundary condition changing operators, which actually sounds, which is a rather complicated name for something rather simple. So if you look at this bottom diagram here, where actually I've already jumped ahead of myself and I've conformally mapped the interior of the curve onto the upper half plane. So now imagine the shaded region is the interior of my curve. Then I'm interested, for example, if I want to calculate ZAB, then I've got to have 4 points around the boundary at which the boundary condition changes from free to fixed to free to fixed to free. And I think of this as the insertion of what I call boundary condition changing operators, which is what I've said here at the top. We imagine, for example, the insertion of a single boundary condition changing operator is, say, going from free to fixed, and I denote that by phi fa. So, for example, that particular partition function that we're interested in, or actually rather the ratio of ZAB to ZFF, can be thought of as a 4-point correlation function of these boundary condition changing operators. Well, that's just a notation, really. But the point is, from the point of view of field theory, these things actually just look like correlation functions of local events. They behave in the same way under scale transformations and conformal transformations, and you can treat them in similar ways.
This statement is kind of axiomatic and article of faith.
Well, if you believe some of the basic tenets of conformal field theory, which I'm about to write down here, which I'm about to show you, then these apply equally. Once you understand what those are, these apply equally to these correlation functions of boundary condition changing operators as they do to ordinary correlation functions of the spins or something like that. This is in 2 dimensions, of course, where a boundary condition changing operator occurs at a point on the boundary. In high dimensions, this would not be true. So what conformal field theory does, I hope you can read this, is to assume the existence of the continuum limit. Okay, so that's something obviously that needs to be proved. But the idea is that if you take some local operator, say phi, and you suitably rescale it by a power of the lattice spacing, take the lattice spacing to 0, then the correlation functions of this quantity have a finite limit, as long as you choose this so-called scaling dimension x in the right way. Conformal field theory also asserts that this scaling limit is also conformally covariant And conformal invariance really comes from a local scale invariance. The idea that because this limit exists, we could in fact choose delta to be slowly varying, and the limit would still exist. That's the idea of how you go from scale invariance to conformal invariance. Okay, so that seems reasonable at least. And then, so some quantity like this, under some conformal mapping, z to z prime, just scales according to the Jacobian of the transformation, raised to the power x. Now, it's quite interesting, though, in the particular boundary condition changing operators that we're interested in, their scaling dimension in general depends upon q, but if you evaluate it at q equals 1, which is what we're interested in doing, the scaling dimension is in fact 0, and it's quite easy to argue why that should be the case. It's just the fact that all these partition functions are in fact equal to 1 at q equals 1. So they're obviously scale invariant. And that means, in particular, that percolation is special in this case. These correlation functions, things like crossing probabilities, are actually conformally invariant and not just conformally covariant. Most correlation functions are believed to be conformally covariant and therefore slightly more complicated. But percolation is special in this case. And all these other random things that we'll be discussing, I think, in this meeting are somewhat special. And then from that, you can, for example, deduce, using the Riemann mapping theorem, that in fact you could take your interior of the rectangle, map it into the interior of the unit disk, in which case those points C1 through C4 get mapped onto Z1 through Z4, and then things like the crossing probability depend only on the cross ratio of those. So it's just a function of a single variable, and you'd like to know what that function is. So that's quite general for conformal field theory. But something else happens in special cases. Some of these correlation functions are known to satisfy linear partial differential equations. And for the Potts model, particularly at q equals 2, which is the Ising model, we actually know these correlation functions rigorously, and it's known that they do satisfy that. And there's also numerical evidence that it also works for q equals 3. So it's a good guess that it works for general q, and that was what my guess was. Okay? And so the way that you derive these differential equations, very briefly, is that you consider some kind of infinitesimal conformal transformation that looks like this. Okay, so we've got our points Z1, Z2, Z3, Z4. We consider this transformation, which is a fine conformal transformation around the point Z2, Z3, Z4, but obviously blows up at Z1, so it's not analytic there. So something else. So we know how phi of Z1, Z3, Z4 transform. They transform according to this rule up here. But phi of Z1 becomes something new. It becomes a new operator in the theory in general. But you can show that it's dimensionally consistent with it just being proportional to the second derivative of phi. So in a general conformal field theory, this is not always true, but for the q equals 2 and q equals 3 Potts models, it's known that this is indeed true. So let's guess that it's true for q equals 1. And then, of course, we have a differential equation for this correlation function. And it's a second-order linear differential equation. And because this only depends upon one variable, it's a second-order linear ordinary differential equation. And, in fact, it's a hypergeometric equation. No, for general, well, for the, I need it for general Q. Okay, so I'll tell you, thank you. So here are the kind of results that you get, and they're kind of messy, so So this is done for general Q, and x is the scaling dimension of that operator. We have two independent solutions of that equation. It's a second-order equation, and by their values as eta goes to 1, you can identify one as being proportional to ZAA, the other proportional to ZAB, and then get the constants of proportionality fixed by the behavior as eta approaches 0 of the boundary condition changing operator. X goes to 0 as Q goes to 1. Okay? So if, for example, you're interested in the crossing probability, then you just take the difference of these two things at Q equals 1, and you get this formula here, which is the formula which I wrote down in 1991. And, of course, if I'd been smart at that time, I would have realized that this particular hypergeometric function is nothing but the conformal mapping of the half-plane into the equilateral triangle, and that so that if you express this problem in the equilateral triangle, it looks very simple. And that's what Vanderlyn talked about yesterday. However, if you look at the mean number of clusters, then you've actually got to take a derivative of these hypergeometric functions with respect to Q. And X depends upon Q, so you get more complicated things. And so this is the final result here that you get. And this thing comes from taking a derivative of the hypergeometric function with respect to its argument, one of its arguments. So it's not a hypergeometric function itself. And the interesting thing, of course, is that you don't yet know how X depends upon Q, but you can get the dependence because in the limit eta goes to 0, these two things have to agree, because as eta goes to 0, the probability of having more than one cluster is very, very small. So in that limit, these two things have to agree. So by comparing these two formulae, you find this number, x prime of 1. So that's something that I've noted here. X prime of 1 turns out to be square root of 3 over 8 pi. Okay? You can get it by Coulomb gas methods as well. And it agrees. Okay. One interesting thing is where do all these factors of 1/3 come from in the arguments of the hypergeometric function? They come just basically because there is always a solution which is a constant, so one of the indices at each regular singular point is 0, and the others are all equal, and you know that the indices of a Riemann equation have to add up to 1, so each of these alphas has to be a third, and it's as simple as that. So that's where all these factors of a third come from this point of view. Of course, from Smirnov's point of view, they come because you're working on a triangular lattice, so, I mean, it would be very interesting to understand the connection. This number, x prime of 1, tells you in the limit when L gets very large as compared with W, then the number of crossing clusters is proportional to L, and it tells you, and therefore inversely proportional to W, and it tells you that the number is then square root of 3 over 4 times that. Let's see, how am I doing for time? I started a little bit late.
So we are now into the question period.
Okay, so I could talk very briefly. Yes, and I think I will, because this links up a little bit with what Smirnov might say. You can talk also about things in the bulk. You can ask, you can take 2 points in the bulk. How many percolation clusters separate those 2 points? And an interesting way to work that out is to randomly assign an orientation to each loop so that there's a current flowing either clockwise or anti-clockwise around the loop, and call that the density of that current J. And then you can define a height function, which is shown on the next picture. Okay, so here's P1 and P2, and I've got these holes, which are the boundaries of the clusters. Going between them, they're randomly oriented, and then I've got these integer-valued heights defined once I've defined the orientation of the clusters. And what you can assert using ideas of conformal field theory is that the probability distribution of these heights in the continuum limit is just given by this simple Gaussian weight with a certain constant here, and that's the and it's fixing this constant, which is a hard thing. This, I should say, is not the ordinary Coulomb gas, but it's a variant of it to the experts. So from that, you can work out that the expected number of holes that thread between P1 and P2 is, in fact, the variance of this object H, H2 minus H1, and it's proportional to the logarithm of the distance between these 2 points with a constant of proportionality k, which is given by this number here, which once again involves square root of 3, but in the denominator, not in the numerator. Okay, I shall stop there, and just let me flash a whole list of references. I just want to point out that much of what I've talked about today is explained in great detail in these lecture notes, which I've just put on the web. Thank you.
Thank you very much for the lightning introduction to the subject. Question?